Our brain is truly marvelous. Billions of neurons communicating each fraction of a second. The question is, how could it evolve? Welcome to Psyched. Previously, we have seen how animals developed a sense of smell and taste to pick up chemicals which provide information about our invisible surroundings. Indeed, natural selection has driven many predators to become masters of camouflage, and sensing the invisible is therefore crucial for survival. Yet, detecting odors of an adversary is limited by environmental circumstances. Competing smells and wind direction have a strong effect whether an animal can avoid becoming prey. Therefore, another sense, the sense of hearing, evolved, which allows an organism to catch pressure waves that result from vibrations in the environment. So, even if a predator is able to suppress the dispersion of a scent, any type of movement will create at least some sound, no matter what the assassin's ambush skills are. On top of that, hearing allows for detecting natural dangers, which are without odor, such as falling rocks and branches. Additionally, producing sound deliberately opens the door for communication, allowing animals to signal intent, such as affection, joy, or antipathy. Humans have perfected this skill by the innovation of language. As we will see, particularly mammals have developed a marvelous sense of hearing. Therefore, compared to many other animals, humans by no means have bad hearing. Nonetheless, some species evolved a sense of hearing that is so amazing humans can only replicate it with technology. Rats, as well as various other mammals, have a broad hearing range, enabling them to detect pressure waves humans identify as ultrasound. Some mammals, such as dolphins and bats, exploited their ultrasound hearing abilities to develop echolocation, which is the ability to map surroundings by hearing where sounds are being reflected. When observing these fascinating capabilities, one question arises: how did the sense of hearing evolve? The cells in our ears that translate sounds into an electrical signal are so-called hair cells. Although the exact mechanisms are complex, basic principles of how hair cells work are very straightforward. Sound waves are tiny fluctuations of pressure in the air or water. This fluctuation in pressure causes the cilium of the hair cell to bend. The cilium is the so-called hair of the hair cell, which is just a slender extension of the cell and not related to the hairs on your head. Bending the cilium induces an electrical signal, which travels to the brainstem and higher auditory areas. So the hair cells are like mechanistic levers, which is why they are categorized as mechanoreceptors. Evidence from modern species of fish, such as lamprey, suggests that hair cells evolved at least 430 million years ago in vertebrate animals. Invertebrate animals also have different types of mechanoreceptors. It is currently uncertain in how far these mechanoreceptors of invertebrates are related to vertebrate hair cells. But it keeps open the possibility that the origin of hair cells lies even earlier in our ancestry. Sound waves traveling underwater cause a small displacement of water particles. In our earliest fish-like ancestors, as well as in modern fish, hair cells act as a displacement detector. Given this feature of detecting displacement of particles underwater, some hair cells specialize in the detection of sound, whereas other hair cells specialize in detecting imbalances. For us humans, detecting sound and detecting a change in equilibrium seems like complete separate senses. Yet, for fish, this may be different. Sound produces small, high-frequency moving particles underwater. But a larger displacement of water can push a fish in any direction, and therefore induce an imbalance. So when you think about it, whether something is a sound or is related to balance for a fish is determined by the frequency of the wave. It is for that reason that hair cells in fish can not only be found in ears, but also in the lateral line along the length of the body. Thus, sensing sound and sensing imbalances is distinct to a much lesser degree in fish, as well as in our earliest underwater living ancestors, which explains why, even in humans, hair cells are involved with both of these senses. For a hair cell to be activated by sound pressure, a reference point is needed. This is why our underwater living ancestors evolved otoliths in the inner ear. These are small, calcified structures that somewhat resemble a little stone. When sound enters the inner ear, the movement of the otolith lags behind due to its greater density, which bends and activates the hair cells. Fossils of otoliths date back to 380 million years ago, suggesting that they appeared not long after the first hair cells. Modern humans still have otoliths, although their main function has shifted towards the detection of balance, gravity, and linear acceleration. Together with the evolution of hair cells, the first brain structures evolved that process auditory information. Two ancient structures in the brainstem that receive input from the inner ear are known as the octaval nucleus and the torus semicircularis in fish. In us humans, we can find very similar structures, so-called homologous structures, and they are known as the superior olive and inferior colliculus. Together, these ancient brainstem structures are crucial for the basics of hearing. That is, where sound comes from and what frequency it is. The way in which these brainstem regions extract this information is simple, yet brilliant. Since we have ears on both sides of our head, a sound that comes from one direction enters one ear a fraction of a second earlier than it enters the other ear. For example, a sound from the right enters the right ear first. This small time difference, referred to as the interaural time difference, is calculated by the superior olive, giving an indication which side a sound is coming from. Furthermore, an analysis of whether sound comes from above or below is performed by detecting small differences in frequency. These differences in frequency are produced by the shape of the ear, which is why mammals eventually evolved an outer ear, or a pinna, to improve vertical sound localization. The processed information from the superior olive is sent towards the inferior colliculus. The inferior colliculus further refines frequency and interaural time difference information. Additionally, it is suggested that the inferior colliculus is the first of many regions that is crucial in integrating a sense of hearing and a sense of touch. On top of that, some connections that leave the inferior colliculus go to movement-related nuclei, and thus produce hearing-related movements. So, whenever you turn your head reacting to a sound, that all starts in the inferior colliculus. When our ancestors left the waters for a life that took place predominantly on land, our hearing apparatus had to adapt accordingly. It is at this point where we see the development of a middle ear, also known as the tympanic ear. Part of the middle ear is the tympanic membrane, which is better known as the eardrum. The evolution of the eardrum was crucial for picking up sounds that traveled through air rather than through water. The eardrum vibrates in response to pressure from sound waves in the air and is connected to little bones. Well, in our earliest land-living ancestors, as well as in modern species of reptiles and birds, the eardrum is connected to just a single bone, the stapes. The stapes acts like a lever that is itself connected to another membrane, the oval window, which forms the connection between the middle ear and the inner ear. As such, the stapes act as a transition between the air where sound comes from and the fluid of the inner ear. Pressure from sound waves causes a vibration of the eardrum, which in turn, via the stapes, moves the fluid of the inner ear. Together with the arrival on land and the formation of the middle ear, the inner ear changed significantly as well. The fluid-filled cavity of the inner ear, containing the receptive hair cells, started to elongate, forming a tube-like structure. This tube-like inner ear structure is known as the cochlea. By having the hair cells placed along a tube, a larger range of frequencies can be detected. Lower frequencies, with slower and larger sound waves, travel further in this tube, whereas higher frequencies don't travel as far. Thus, the hair cells along the cochlea are responsive to different frequencies. The longer the tube, the larger the frequency range that can be detected. This is why later in evolution, we see that the cochlea curls up, forming a snail-shaped structure that we recognize in many living mammals, and indeed in humans. A broader range of frequency information requires more computing power. This is why we see the arrival of the cochlear nucleus in the brainstem, which performs initial processing of sound frequencies. Additionally, at the dawn of the first mammals, we observe that structures of the thalamus specialize to processing sound, specifically the medial geniculate nucleus. The medial geniculate nucleus contains neurons that are highly frequency specific and specialize to changing sounds, which allows an animal to direct attention to moving predators or prey. By the time we observe the transition from mammal-like reptiles to the first true mammals, around 200 million years ago, another change occurred in the middle ear. Two small bones that initially were part of the jaw in earlier synapsids started to separate from the jaw. These two bones, the malleus and the incus, conjoined with the stapes in the middle ear. As such, the middle ear of mammals contains 3 bones rather than just 1, as is the case in reptiles and birds. These 3 bones act as an amplifier to augment incoming sound waves, making it easier for mammals to detect even very small sounds. But there is more. Mammals acquired yet another feature that sharpened their sense of hearing: the development of an outer ear. Although mammals have outer ears in all shapes and sizes, the function is always similar: reflecting incoming sound waves and funnel them towards the middle ear. This is why even faint sounds can be picked up, and different frequencies related to sound coming from different directions can be distinguished more easily. So as soon as the first mammals arrive, we see multiple changes in the hearing apparatus. Sound amplification of 3 bones in the middle ear system, an elongated cochlea, and the development of an outer ear. This also meant that the information obtained from sound skyrocketed in mammals. This increased signal complexity therefore coincides with the development of new brain structures. As we have seen previously, mammal evolution is characterized by the emergence of the neocortex, containing regions of various senses. As such, one crucial neocortical structure evolved for processing sound, the auditory cortex. The auditory cortex can be divided into the primary, secondary, and tertiary auditory cortex, also known as the core, belt, and parabelt. Just as other regions we discussed before, a tonotopic organization can be observed where different frequencies relate to different areas of the auditory cortex. This is most clear in the primary auditory cortex, which responds most strongly to pure tones. However, this tonotopic organization is somewhat blurred in the belt and parabelt regions, since these areas respond most strongly to more complex sounds, containing a full range of frequencies. An example of sounds containing such complex frequencies are vocalizations, which an animal uses to communicate. Being able to distinguish vocalizations from fellow members of your species is crucial for survival, as it allows for signaling dangers, showing affection, and conveying displeasure. Yet, simply being able to hear complex vocalizations is not enough. An animal needs to be able to conceptualize sounds. For example, an animal needs to understand that a high-pitched squeak implies danger, whereas a soothing rumble means that a mate shows affection. In other words, complex sounds and vocalizations need to have meaning. Therefore, secondary and tertiary auditory areas are connected to regions in the medial and superior temporal cortex. These areas conceptualize sounds and give them meaning. In humans, such areas have developed dramatically, allowing us to develop language. We are able to give semantic meaning to thousands of words. And by combining words in a sentence, we are able to basically have an unlimited amount of sound combinations that make us able to explain the world around us. In the last 4 episodes, we have seen how the senses evolved, providing us and other animals to experience the world and its wonders. Although our senses are a prerequisite for such rich experiences, having an awareness of ourselves and others requires more than just the senses alone. Therefore, in the 5th and final episode of this series, we will unravel the mysteries of consciousness and how the evolution of more complex brains allowed for increased richness in comprehending our surrounding reality. So, we hope you enjoyed this episode, and we hope to see you the next time.